Hey there everyone, welcome back. So this video will be a short overview or a short intro to what energy kind of is, right? And why we have a conservation principle for it. So I hope you watch this video before doing the examples later on, all right? So in your studies so far, in Chapter 7 and Chapter 8 up until this point, have you come up with an idea in your head of what energy actually is, right? Have you? It's okay if you haven't, because I'll be honest in that I personally don't know what energy is, okay? And that being said, physicists don't break up energy into, say, tiny bits. We don't have particles of energy, so to speak, right? We have either electrons, we have protons, right? But they're not pure energy. We don't have a concept of what energy is. So energy to a physicist is a purely abstract concept. We've come up with ways to quantify how much energy a particle or an object has, right, at certain points in space. And also, more importantly, we've come up with ways to quantify an object's change in energy, right, to get a better idea of what's happening to that object. So we can quantify how much energy an object has, but that's really abstract, right? We can say a particle has 10 joules of energy, right? Well, what does that 10 mean? Well, we've quantified, we have a definition of mass, right? That comes from the kilogram, which as of May of 2019 has been defined by a physical constant, right? An unchanging physical constant named Planck's constant. You'll cover that in 4C. The local acceleration due to gravity, little g, that's pretty much always constant, right? That's unchanging on Earth. And say the distance that some object moves, well, that can be well defined as well. The speed can also be well defined based upon the units of meters and seconds, also defined by physical constants. So physicists give objects energy based upon purely, I'll say, made up mathematical constructs. But what is energy? I don't know. Okay? For example, let's say you fire some projectile up into the air, right, with some initial speed, whatever it is, right? You know from previous chapters that it'll arc up and land a horizontal distance away, okay? But the energy that it has initially, and I'll write this as E, because I'll show you in a second why, the initial energy has to be equal to the energy at the top, right, at some final position. But this initial and final position, both of them are purely arbitrary, right? Those 2 points are completely arbitrary. I just picked them in this example. I could also choose this point here when an object starts there and when it ends over here, right? Initial and final here and here, the change in energy between these 2 points will be the same as what it was from here to here, right? In essence, the change in energy is 0. That may be confusing, right? The total change in its total energy is 0 between any 2 points, assuming there is no non-conservative forces acting on it, like in this case, air resistance, okay? So when an object starts at this point, which I'll call A, right? And let's say up here at point B, it has a different speed. Well, what's happening to its overall energy? Well, initially, the kinetic energy, it has some initial kinetic energy, 1/2 mv squared, and as it moves up in height, right, that speed or that kinetic energy will decrease, right? The vertical speed the vertical component of this initial velocity will get smaller and smaller until eventually it's just zero, right? The horizontal component won't change, but the energy overall, I should make that a vector, will decrease to some minimum value right there. But if the kinetic energy goes to a minimum, what has to go to a maximum in order for the energy overall to be zero? Well, let me put it this way. The kinetic energy at A, let's see here. Kinetic energy is maximum. And up here, we'll have K is a minimum. Okay? What has to increase such that the overall energy is zero? Well, it's the potential energy. And this depends on its height, right? So at point A, if, say, we measure this to be, let's say, y equals 0, we can say the potential energy is 0, sure, but it's at a minimum value. Up here at point B, U then has a maximum value because now it's at some height of, h, we'll call, or y final, whatever you want to say. In other words, it has a maximum height. So as potential energy decreased, as kinetic energy decreased, potential energy increased, such that if we were to add both of these together, the overall energy is the same from start to finish. Okay, so let me draw that right here. Let's see. Initially, at point A, let's do it like this. At point A, we have kinetic energy, potential energy, and the total energy, right? This is at point A. So kinetic energy is at a maximum value. Let's do bar graphs now. Potential energy is at 0. So right there, 0. And so if we add these up, we get a total energy of whatever it is, right? At point B, let's do it over here. Point B, we have the same things. Kinetic energy is a little less, right? It's still moving, so it still has some energy of motion, but now the potential energy is increased by the difference, such that if we add these up now, we still get the same amount of total energy. All right? So what's happening is that the energy is simply changing forms. It's changing from purely energy of motion into some combination thereof, right? And then as it decreases height, guess what? It speeds up again, and so the energy that was potential goes back into being kinetic, and thus it speeds up. Okay? Then this analysis can be done between any 2 points, right? Any 2 points. So this conservation of energy, in that it's constantly moving, constantly changing from one type into another type and back and forth, right? Such that overall, the total energy E is 0. That's the concept here, right? And so it's not only E equals K plus U, it's the change, right? It's the change that's important, okay? The change here. And so remembering back to previous videos, actually I'll put 0. Previous videos said that there are forces that do work on objects, right? Namely conservative forces like the force of gravity that does work on an object. So let's take the force of gravity. As this particle would go from point A to point B, the work done by gravity is positive delta K, right? Gravity does positive work on it in trying to slow it down. it would also do negative work on it. So it would have a negative delta U. If we combine these two together, right, we have simply this. So let me write this another way. Let me move to another slide. So we have positive delta K, that's the change in kinetic energy, and that equals negative delta U. That's the negative change in potential energy. And this is the work done by a conservative force. So let's write that by work conservative. In this case, it was gravity. And so let's write out these expressions. 1/2 mv final squared minus 1/2 mv initial squared equals negative mg, I'll say y2, minus a negative, so that's plus mgy1. Actually, let's keep it initial and final. And now let me put all of the initials on one side and all of the finals on the other. All right, so let's see. This one goes over there, and this one goes over there. So we have 1/2 mv final squared plus mg y final equals positive 1/2 mv initial squared plus mg y initial. So this says that the total initial energy equals the total final energy, right? And I'm using E here as the total. And this is the conservation of mechanical energy, right? Or conservation of energy, right? I should say that I think your book uses mechanical in this case to denote the sum of K plus U, okay? And so for non-conservative forces, right? Remember, non-conservative forces are such that the net work done is 0. We have the conservation of energy, which can be written delta E mechanical equals 0, and that's equal to delta K minus delta U. Okay? For non-conservative forces, right? Non-conservative forces, energy is not conserved. Energy is not conserved. And so we have, for work non-conservative, you have plus delta K plus delta U, that should be a positive right there. And this has to equal that force times the distance, right? The non-conservative force times that distance. And again, this force can be, for example, kinetic friction. It can be air resistance, right? In this chapter, we'll pretty much always worry about kinetic friction as this non-conservative force, right? We won't really talk about air resistance, and we won't talk about any other non-conservative forces, okay? So this is for the work done by non-conservative forces. It's not conserved. It's not 0, right? This is not 0. It does depend on that path taken as to the amount of energy that is given off. Whereas up here, this is for conservative forces. The total change is 0, okay? So 2 distinctions, all right? So keep this in mind in later examples when I'll be solving for conservation of energy, right? I'll be using that concept to solve for various quantities, all right? All right, thanks for watching.